All right. So, first of all, I want to say I am sorry that I forgot to tell you I am not going to be here today, but as you can see, I am not here today. I'm actually at home in bargaining meetings. Yay! So, I'm on the bargaining team for the district or for the teachers. So, anyway, that's what I'm doing today. Very exciting. I'd rather be there with you guys. But important, you still can turn in any homework that you want to go on this grading period. This hopefully the sub told you that, but just in case they didn't, you can turn in your homework. Give it to the sub. They'll leave it on my desk so that I can get it when I get to school on Tuesday morning, and I will have time to put it in the grade book before the grades go out. So there's that, and even better, dun, 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 there is a change in the schedule. So I'm going to warn you, tonight's homework is kind of long, and I apologize for that. Um, I'm using a homework packet that another teacher had made, and it's really good. And I had just, glanced through it, but obviously I didn't have enough time to work out all the problems before giving it to you guys. And tonight's homework is a little excessive, I think. Every problem is really good though. So there's no busy work in it. It's just long. And also Mr. Nguyen's kids, unfortunately already started working on it. So it was too late to change it, but it is worthwhile. So I don't have a problem with still assigning it, but I do have a problem without giving you guys a work day. So I'm giving you guys Friday as a work day to work on it. And Mr. Nguyen's kids also have a work day, but everything is going to get pushed out a day. So your test is now scheduled for October 3rd. And Canvas will be reflected to show this as well. But I do want to point out that this is a work day, not a free day. I do expect you are working on something academic. It's okay if it's not calculus, although I prefer it to be, but it must be academic. You cannot use it to play games or do whatever. You won't be able to use your phone. It is a work day. Okay, enough said about that. Let us get into the lesson. So, one thing with today's lesson, in order to get the most out of it, you will see this message periodically. I really encourage you to do exactly what it says. Pause the video and answer the questions before moving on. You'll get a lot more out of it. And even better is if you can get the people that are sitting near you to do the same. And then you guys could talk about the problems together. But at least do it yourself. So with that said, it does say pause the video and answer before moving on. So pause the video, and when you're ready, unpause, and we'll do these together. Okay, hopefully you really did pause the video. I'm just going to quickly show you some examples for A where the function value exists, but the limit doesn't. I mean, one really easy one is maybe you just have a point at x equals 5, and that's it. Obviously, there's no limit then. You could have something like this where maybe there's a gap in there like that. Or you might even have something like this where maybe there's an asymptote at x equals 5. So on one side it acts like an asymptote, but maybe on the other side it doesn't, and you have something like that. There's all sorts of different possibilities, but those are just a few, where the function value exists, but the limit does not. Now, let's flip it. Let's look at something where the function value does exist, but the function value does not exist, but the limit does. So if the limit is going to exist, then it's going to have to approach the same value from both sides. But if the function value does not exist, then we just have a hole. And you have something like this. All right. So just, kind of putting some seeds in your brain, starting to wire it to think about continuity. But let's look at these now. Let's look at the types of discontinuities. So there's actually two big categories, removable and non-removable. Now, removable discontinuities, these are actually just holes. And you might have something like this where there's a hole and the function value doesn't exist. Or maybe you have something like this where there's a hole and the function value does exist just somewhere else. they're both considered removable discontinuities because all we need to do is either fill the hole or redefine the function to fill the hole. So it's removable. Non-removable discontinuities come in three flavors. So one flavor is called a jump discontinuity. And it's kind of like what it sounds. The graph makes a jump. And, you have something like this. That's a jump. Or again, it could be open here. It could be solid. The graph is making a jump. Another one is called an infinite discontinuity. This is also considered non-removable, and that's just an asymptote. And it's called an infinite discontinuity because as the function approaches that asymptote, the graph is going towards positive or negative infinity. So these are called removable discontinuities because you can either define a point or you can redefine a point. But if you have something like these non-removable ones, you can't just remove the discontinuity by redefining a single point. So these are non-removable. So those are types of discontinuities. Just gives us some vocabulary to talk about things. Oh, look at that, another pause video. So what I want you to do using those, see if you can determine the points of discontinuity, what values of x is the graph discontinuous at, and determine the type of discontinuity. And when you're ready, go ahead and unpause the video. All right, so for the first one, we can see that we have a vertical asymptote at x equals -2. So that is an infinite discontinuity at x equals -2. And remember, it's not a common factor, so whatever makes the denominator equal 0 is going to be a vertical asymptote. All right, for b, we're going to have to factor first and see if anything cancels. So if we factor, this will factor in the bottom like this, and oh, the x minus 1's do cancel. So this will simplify to this as long as x doesn't equal 1. So what does this mean? We actually have 2 points of discontinuity. We have a hole at x equals 1. So that means we have a removable discontinuity and we can actually even find the coordinates of the hole. So the x value is 1, and then if you put 1 into the simplified version, you're going to get -1/2 for the y coordinate. So we have a removable discontinuity at that point, and then there is an infinite discontinuity where there's a vertical asymptote, which is at x equals 3. And then finally, I don't know if you remember this graph, it's our good old friendly graph that keeps coming up. This is the one that looks like this. It's equal to +1 for the positive real numbers, and it's equal to -1 for the negative real numbers. So that means we have a jump discontinuity at x equals 0. And remember, this type is non-removable. This is removable. This is non-removable. This is non-removable. All right, let's see what we got next. So now for the definition of continuity. I mean, we have a rough idea already. I mean, it's continuous. You can draw it without picking up your pen. That's continuous. If you have to pick up your pen to draw it, it's not continuous. Yeah, true. But we have a formal mathematical calculus definition. There's three components to this definition. So, I mean, honestly, if you want to, I don't have the pause of video, but if you want to think about it, like I said, there's three components. Can you figure out what the three components are? But let's look at them. Oops. Oh my goodness. There we go. So first of all, in order to be continuous at a point, the function value has to exist. Secondly, the limit has to exist. Now, can you think of a graph where the function value exists and the limit exists that's not continuous? And you could have something with a hole where it's defined elsewhere. So now we have to fill the hole, and we're going to fill the hole by saying the function value is equal to the value of the limit. And once you have that, that's going to fill the hole for us. And so that's it. That's the definition of continuity. And it makes sense, but in some problems, there's work. Some, there's not much work. But you do need to state these three things. I am going to be looking for these three things. The AP exam is going to be looking for these three things. I have seen them ask about continuity on the FRQs before. So I do, and we're going to be looking at plenty of examples where you'll see me listing out these three things. Now, these first two things can be done in either order. You can show the function value exists and then the limit, or you can show the limit exists and then the function value. It doesn't matter. But obviously, you need to do these two before you show this one. And I do want you to show these two separately. You may think, well, I'll just do this. And it's not good mathematical form. We're going to separate it out and make sure that we have all three things distinctly shown. So I'm just going to say do it. I'm going to be looking for all three of these. In fact, ideally, you're numbering them. But like I said, it doesn't matter if one is that the function value exists and two is the limit, or maybe you switch these. That doesn't matter. But do these two first, and then this is really easy. So, okay, so now let's take a look at these. So we've got, it does say pause the video, and so I encourage you guys to do that. You may be going, though, wait a minute, what does she mean by extended function? I've never heard this before. You may not have. I haven't used it yet this year, so if you haven't you heard it in previous years, all it means is this. I'm going to go back, actually, to this part right here. When we were doing part B, remember, y is equal to this, but it is also equivalent to this because we're specifying x can't equal 1, because x can't equal 1 in this blue version. Well, if I just wrote this, this is equivalent to the graph of the blue function. It's just the blue function has a hole, but the green one doesn't. This is considered the extended function. It's the same function with some extra, at least one extra point in it. So it's an extended function. So see if you can find the extended functions for this that would make it continuous. So pause the video, give it a shot, and we'll look at it together. Okay, so first of all, I don't know if you guys remember, but the limit as x approaches 0 of the sine of 5x over x, it's almost that identity that I gave you, but we need a 5 down here so that this matches this up here. But if I divide by 5, I also have to multiply by 5 to keep things equivalent. And so now this is the same thing as saying 5 times the limit as x approaches 0 of the sine of 5x over 5x, which is 5 times 1, which is 5. This graph right here has a hole. The limit exists, So the limit as x approaches 0, it means on either side, who knows what the graph actually looks like, but at x equals 5, actually, at x equals 0, on either side, the graph is there. There's just a hole because the original function, we can't let x equal 0. So how do we fill that hole on this one? Well, unfortunately, we can't do something like above and cancel out common factors, so we make a piecewise function out of it. We can say that y is equal to the sine of 5x over x as long as x doesn't equal 0. And then to fill the hole, we need to define the function value at 5 when x does equal 0. And there's our extended function right here. I do want to point out that this is h of x. Notice I did not call this h of x because h of x has a hole. I have just filled the hole here, so it's not the same function. So I'm just calling it y, but don't call it h of x. Your homework tonight, the answer key actually has the questions about writing an extended function called the function the same thing, and it really shouldn't have, because this function is different from this function. This has one extra point than this one does. So they're close, but they're not the same. Okay, let's look at k of x. So k of x, if we tried to plug in a 4, it would make the function undefined. But if we did this, multiplied top and bottom by the conjugate, then we will get something to cancel out. So on the top, we just have x minus 4 times root x plus 2. But on the bottom, remember when you multiply conjugates, when you multiply a minus b times a plus b, it's a squared minus b squared. So it's just going to be x minus 4. And then these will cancel. And so k of x is equal to root x plus 2 as long as x doesn't equal 4. Well, in this one, since we canceled out a common factor, we can just say our extended function is y equals root x plus 2. We won't put this, ooh, I forgot to put that, not equal to. We won't put this in there. This is what creates the hole when we write it this way. Just leave that out, and now the hole is filled. So there's our extended functions. Okay, so here's just some notes for you. So the reason why continuity is so important is there's going to be a lot of things we do in calculus that depend on knowing that the function is continuous. So it's a big deal. And so you will have to sometimes state or figure out if a function is continuous. Well, polynomials, sine, cosine, absolute value functions, and exponential functions automatically continuous. You don't have to prove them continuous at all. You can just say it's polynomial function, it's continuous. And even better, if you have any kind of combinations of these. So if f and g are already continuous, then any kind of combination of continuous functions is continuous. Elementary though. So you can add or subtract or multiply or divide them as long as the denominator doesn't equal 0. And you can even multiply a continuous function by a constant and it's still continuous. So just something to kind of keep in mind there. Pause the video if you need to write this down, and I'm going to move on. Oh my god, another pause the video. Okay, so now that we've done that, try to think about this one, and you should be able to do this one. So give it a shot, and then we'll come back and look at it. All right, so we have g of x. It's got 5 pieces to it, and we can see the 1, 2, 3, 4, 5 pieces. So let's see. Does g of 1 exist? Well, g of 1 does exist. It's right down there. So yes, it does. Does oops, sorry. Does a limit exist as x approaches 1? And yes, it does. It's approaching the same value on both sides, so yes, it does. Does the limit as x approaches 1 of g of x equal g of 1? And the answer is no. Unfortunately not. The function value is down here at 2. The limit is right here at 0. So they are not the same. So is g continuous? And the answer is no. We can clearly see it from the graph that is not continuous at x equals 1. We cannot draw the graph without picking up our pen, but by definition of continuity, we can also say it is not continuous. Okay, so now try these. Okay, so now we're looking at -1. Is g defined at -1? And here's x equals -1. And no, it's not. So is g continuous at x equals -1? No, it's not. No, because g of -1 doesn't exist. It's already failed one of the three conditions. If it's failed one of the three conditions, you can just jump to saying no, it's not continuous, because it's not. All right, here's a couple more. Okay, so for the first one, what values of x is the function continuous at? Well, it's continuous basically everywhere that until I have to pick up my pen. So it's continuous, and then here's another place it's continuous, but then I got to pick up my pen. Here's another place it's continuous, and then it can't really be continuous when there's just a single point. So, but then it's continuous here. So we have the interval from -2 to -1, and the interval from -1 to 0, and the interval from 0 to 1, and the interval from 1 to 2. And there it is. What value should be assigned to g of -1 to make the extended function continuous? So here's where -1 is. We need to fill this hole. This hole is at y equals 1. So what value? Well, we should define g of -1 to equal 1. And that would fill the hole. That would make it continuous. How should we redefine g of 1 to make it continuous? Well, we need to fill this hole. So we need to move this point up here and redefine it to be equal to y equals 0. So we need to say that g of 1 equals 0. Okay. Last question about this graph. Is it possible to extend g to be continuous at x equals 0? And remember, when we say extend g, we're just talking about redefining or defining a point. And if so, what value should be extended? And if not, why not? And the answer is no. G of x cannot be extended to be continuous at x equals 0 because there's a jump discontinuity. G of x cannot be extended to be continuous at x equals 0 because there is a jump discontinuity. At x equals 0. You can only extend functions to make them continuous when there's holes, when there's removable discontinuities. Not non-removable. That's why we call them non-removable. It's a discontinuity that we just can't fix. Okay. I just have a couple more problems for you. So there's this one. Now, this one has a slightly different message. Pause and think about it, but we're going to work it out together because this is going back to the definition of continuity where I said there's those three things. And I want to make sure that you format in a basic way. I'm not going to make you do it exactly my way, but I'm going to just remember you have to show the three things. You have to show that the function value exists, the limit exists, and that they are equal to each other. And I want you to do those three things separately. So think about that and do as much as you want before we do this together. Okay, so we have a piecewise function. And so something could be happening on one side of t equals 1 than the other. So when we do the limit part, we're going to have to do a two-sided limit. So let's see, does f of 1 exist? That's our first condition that we need to show, or one of the first two conditions we need to show to see if it's continuous. And since 1 is defined here, we can look at this piece. So f of 1 is equal to 1 squared plus 5 times 1 minus 4, which would be 2. So yes, there is a value, which means f of 1 exists. All right, 2. Does the limit as x approaches 1 of f of x exist? And like I was saying, because this is a piecewise function at t equals 1, we're going to have to do left and right hand limits. So does the limit as x approaches 1 from the left equal the limit as x approaches 1 from the right? Well, from the left, when we are approaching 1 from the left, that's when t is less than 1, so we're looking at this piece. So that's going to be t squared plus 5t minus 4. And then when x is approaching, I really should be using, oh well, actually it doesn't matter. Here's a little lesson. I'm using x's here, but it actually doesn't matter. This is t, I've just changed a variable to x. It's still the same function. I'm just not mixing up the t's and x's within the same lines. So I'm actually I am just now, aren't I? I need to change these to x's if I'm going to do that. Sorry about that. And then the next one is 3. When I'm approaching 1 from the right, that's when t is greater than 1, and that's just 3. So the limit as x approaches 1 from the left, that is going to be 2. This one is going to be 3. They are not equal. So the limit as x approaches 1 of f of x does not exist. Well, if it doesn't exist, what do you think that means? That means it's not continuous. So we can just say that I'm going to switch it back to f of t. F of t is not continuous at t equals 1 because the limit as t approaches 1 of f of t does not exist. Bummer. So, there you go. So I do want you to show that. Shows 1, 2, and then if these were both equal, just to give you what it would look like, if those were both equal, then step 3 would be to show that f of 1 equals the limit as t approaches 1 of f of t, and therefore f of t is continuous at t equals 1. You've shown the three conditions. But We'll let that fade off because this one was not continuous. Okay, last problem. Think about this one. All right. Now I am going to put a little caveat on this. If this was, I mean, you guys could have been, you might have seen problems like this last year in STEM or pre-calc. Um, we're in calculus now, so we're going to give the calculus answer. If it was multiple choice and work didn't matter, honestly, all I would do is set x squared minus 1 equal to 2ax, and then substitute x equals 3 in there and solve for a. It's the quick and dirty way to do it, and you get your answer. But this is not multiple choice, and we are in calculus. We're going to do the calculus answer. And in order for the value to exist, we got to make the limit exist. It's going to bring it back to limits. So we need to show the limit as x approaches 3 from the left is equal to the limit as x approaches 3 from the right. And the limit as x approaches 3 from the left means when x is less than 3, so we're going to look at this piece. And as x approaches 3 from the right, that means x is greater than 3, so we're going to look at this piece. Now to work out the left-hand limit, we can just put a 3 in for x. To work out the right-hand limit, we can also put a 3 in for x, and we get 8 equals 6a, so 4/3 is equal to a. And then that could be it. You will have to do limits, though. I know that you may be going, we didn't do the function value. You're right, we didn't. But I mean, be thankful that I'm letting you get away with not showing the function value. But you do need to show the limits. So, all right. So that's the end of that. And so hopefully this makes sense. And it's the end of the lesson. Have fun with your homework. You can start working on your homework now. And I will see you guys on Wednesday when I get back to school. Bye.